Today's lesson, it's an extension from what we did last time. So remember, what we're working towards is being able to graph rational functions. And there's a lot of things that go into being able to graph rational functions. So yesterday was all about discontinuities in the domain, right? Wherever we divide by zero, we get a vertical asymptote or a hole. The other feature of rational functions is a horizontal asymptote. So we still see that word asymptote just like we saw with the vertical asymptote. Um, but this has a different behavior than the vertical asymptotes, and they show up for different reasons. Okay, so this is, again, just us working towards being able to graph rational functions. And tomorrow, that's what we're going to actually start to piece together. You are going to actually graph rational functions tomorrow, and we're going to work on all three of these things. Okay, so horizontal asymptotes. First, you'll see me just abbreviate it as HA. They're different than vertical asymptotes in that really what they're telling us is what the y value the graph approaches as x goes to positive or negative infinity. So if we look at a rational function, we go all the way to the right, all the way to positive infinity. Our rational function is going to approach a particular value. Okay, it's going to get really, really flat, just like the vertical asymptote. Okay, it's going to get infinitely close to that value, but it won't 100% get there. Okay, so these show up more as indicators as to what's happening as our graph goes to negative and positive infinity, kind of like end behavior. Okay, it almost is a way to describe end behavior. It's just that now our end behavior is not going up or down. It's approaching a particular value. Okay, so it still has that same feature where it's going to look like it gets really close, but doesn't actually touch it. And that's what the next line says. Horizontal asymptotes still work like vertical asymptotes, and our graphs do not touch the asymptote. However, there are actually exceptions to that rule with horizontal asymptotes. It doesn't show up all that often, but every now and again you might see our graph like actually pass through the horizontal asymptote, but then it's going to still eventually get really close to that. Okay, so just know that if you end up crossing a horizontal asymptote when you're graphing these functions, when we piece it together, that's okay. Okay, that can happen. But in general, it's just what are our graphs approaching. All right, so there are three different cases, okay, of how we're going to be able to determine the horizontal asymptote. And it depends on the degree of the numerator and denominator. Degree being the same thing we worked on in our unit of polynomials, the highest exponent. So all we're doing is we are comparing exponents from the numerator and denominator. If the numerator is smaller than the denominator, then our horizontal asymptote approaches zero. If the numerator and the denominator have the same degree, then we're going to approach y equals the ratio of the leading coefficients. And then as n, or if the numerator is greater than the denominator, then there's no horizontal asymptote. Okay, so with this, it might be something you need to memorize. I'm going to explain it in a way where I don't have this memorized. Okay, I think about a different kind of concept to help me decide what's going to happen as we use really large x values or really small x values, okay, to decide what these horizontal asymptotes are doing. Last thing, there will only be one horizontal asymptote, if there is one. Okay, sometimes there's none, but you'll never see a rational function that has more than one horizontal asymptote. All right, like yesterday, we're going to kind of take a look at this graph on Desmos. Let's factor this, and let's also tie in what we had talked about yesterday so we can see all these features on that graph. So first thing is we're going to factor. So I get 2x minus 4. In the denominator, that factors to x plus 1 and x minus 4. Okay, discontinuities in our domain, or domain restrictions, are that x cannot equal negative 1, x cannot equal 4. And so that means we either have a vertical asymptote or a hole at negative 1 or 4. Well, the x minus 4's divide out, so the simplified equation is 2 divided by x plus 1. So since x plus 1 survived the canceling, we have a vertical asymptote at x equals negative 1. And then we have a hole at x equals 4 because those terms canceled out. The y-coordinate of our hole I get by taking this x value of 4 and plug it into the simplified equation. So that'd be 2 divided by 4 plus 1. That would be 2/5, which is 0.4. Okay, so once again, we'll take a look at the vertical asymptote at the hole when I pull up the graph in Desmos. The last thing I want us to think about is what I just introduced, that horizontal asymptote. So for the horizontal asymptote, we're going to go back to the original function, and we're comparing the degree. The degree of the numerator, I'll get to this in a sec. So degree of numerator is 1. Degree of denominator is 2. Okay, so what I think about here is I think about what happens as x gets really big. What is going to happen with these fractions? Well, if I plug in, let's say, like 100, okay, look at just what happens on my calculator. If I'm not going to care about what is actually in my numerator or denominator, I'm just going to focus on like x over x squared. But look what happens. If I take x over x squared, that'd be 100, divided by 100 squared, okay, I get 0.01. Well, what happens if I make that even bigger, like 1,000? So 1,000 squared. Oh, I forgot to do the division button. Okay, I go from 0.01 to 0.001. If I go to 10,000, now I go to 0.0001. Okay, that's the calculator's way of doing scientific notation. So what's happening as x gets really big? What's happening to these values? They're getting smaller, right? I'm going from 0.01 to 0.001 to 0.00001. All these values are getting really close and approaching 0. So how I decide the horizontal asymptote, again, I don't have these rules memorized. I'm like, if I plug in really big numbers, the squaring takes over. Okay, the squaring takes over so that my denominator gets really big while the numerator is not getting big at that fast of a rate. And with fractions, the bigger the bottom is, the smaller this number is going to be. Okay, so since our numerator has a smaller degree than the denominator, our horizontal asymptote is y equals 0. And so that means we're going to see our graph tail off as we let x get really big or really small. And I'm going to take a look at that here in just a second. So again, with the horizontal asymptote, you can memorize the rules or think about what happens if I plug in really big or really small, and by really small I mean very negative numbers, and see what that works out to be. Okay, I'm going to pull up Desmos. If anybody's watching the video, I want you to do the same and plug in the original function of f of x. So this is f of x equals 2x minus 8 divided by x squared minus 3x minus 4. All right, so we talked about, I think this is the same graph from yesterday, but x equals -1. There's that vertical asymptote on that graph. If I keep going up, we're going to see that that line gets really, really close to it, and eventually it looks like it's on that line. But if I zoom in, there's always going to be a little bit of space, and that's what I mean about vertical asymptotes getting infinitely close to that line. Okay, we also identified, okay, I'm getting a lot of side conversations. Those need to stop, please. It's distracting to me. Thank you. I'm also recognizing that there's a hole where x is 4. And remember, that doesn't show up because that hole, it's infinitely small. But it still exists there. So if I click on that point, it says undefined, and it will show that actual gap in the graph. Okay, so there's still a hole there even though we don't see it. The last thing is the horizontal asymptote, so y equals 0. That's the green line here. Okay, you can see that as x gets really big, we're just getting closer and closer to 0. Okay, and that would continue as far over as I go. Okay, but again, properties of asymptotes, oops, I scrolled down too far. There we go. Properties of asymptotes is that our graph gets infinitely close to that value, but it won't actually touch it. So there'll always be a little bit of space between the asymptote and the graph. So tomorrow, when we start to piece this together, we're on your graph. I'm going to be looking for the vertical asymptote, the hole, and the horizontal asymptote, and then we just need to fill in the shapes of the graph. Okay, and that's what we'll work on tomorrow. How can we actually get the shape in between all of these asymptotes? All right. Any questions here before we identify the asymptotes for the rest of these functions? Okay. So now back to the notes, and all we're going to do is just figure out what are the horizontal asymptotes for the rest of these functions. I'm going to do A, B, and C, and I'm going to have you on your groups do 1, 2, 3, and 4. Okay, so once again, we are comparing the degrees of the numerator and the denominator. So here, the numerator, the degree is 1, the denominator is 2. So we'd say that the numerator is less than the denominator. Now, this is helpful if you are going and using the rule. N is less than D, that means y equals 0 is the horizontal asymptote. I don't have that memorized. I, again, think about what happens if I plug in big numbers. If I plug in big numbers, the squaring takes over, and as the denominator gets really big, the numerator is not getting that big. So that makes this get closer to 0. So since the numerator is less than the denominator, our horizontal asymptote is y equals 0. Part B. Now our numerator equals the denominator, right? Degree is the exact same. So nothing takes over, right? The numerator and the denominator are growing at a similar rate. If I plug in big numbers, that big number is getting squared in both places. Okay, so this is kind of the weird one where the value that we end up approaching are the coefficients of, or the leading coefficients being divided by one another. So that's y equals 4 divided by 2, which is 2. So your horizontal asymptote is y equals 2. And then the last one, now my numerator is greater than the denominator. So cubing and squaring, as we cube numbers, the top gets really big. Okay, and if I show you kind of what I was doing in the calculator earlier, look what happens when I take 100 cubed and divide it by 100 squared. Okay, I get 100. If I change it to 1,000, okay, then we're going from 100 to 1,000. So this just keeps growing without slowing down whatsoever. Okay, so again, when I think about x getting really big, the top takes over, and the numerator is going to go to infinity while the denominator stays small. So in this case, there is no horizontal asymptote. All right, any questions with how I'm identifying these horizontal asymptotes or any of these rules here? All right, on your own or in your groups, identify the horizontal asymptotes for 1, 2, 3, and 4. It should take you like 2 minutes. And then that's it for today. Number 1, has no horizontal asymptote. The numerator is greater than the denominator. And again, I'm referring to the degree, the largest exponent. That squaring takes over. So our values, as x gets really big, they don't have any bounds on them. They just keep getting bigger and bigger and bigger. Okay, so that would be kind of like the polynomial where we're going to see it going to positive infinity or negative infinity. Number 2, Now it's the opposite. Numerator is less than the denominator. So that means we approach y equals 0. The denominator gets really big while the numerator gets small. And so our horizontal asymptote approaches y equals 0. 3 and 4, they are both equal the degrees. And so when that happens, you divide the leading coefficients. So you go 1 divided by -2, 2 divided by 1, and that's how you get the horizontal asymptote. Okay, the homework assignment that I gave to you all yesterday has this already built in. So that assignment that you all got, you are identifying vertical asymptotes, holes, and now also the horizontal asymptote based on what we talked about today. All right, that's all I got. If you weren't here yesterday and need the homework, come get it from me. The rest of class time is yours to get some work done.